Hello, everyone. My name is Jordan Dotzel, and I'm a PhD student at Cornell University and a part-time student researcher at Google. And today, on behalf of all of my co-authors here, I will be presenting a quick overview of FLIQS, which is a one-shot floating point and integer quantization search. So the motivation for this work has been the recent explosion in numerical formats. So what I'm showing here is a variety of formats where they are split by their sign, exponent, and mantissa bits to show the trade-offs between precision and dynamic range. And originally, within scientific computing, double and single precision floating point was dominant. However, today, with AI workloads, the highest precision typically used, at least during inference, is 16 bits. So this includes often FP16 and the BrainFloat format from Google. And even more recently, we've been pushing to lower bit widths, including 8-bit variants, 4-bit variants, and even, in some cases, binarized neural networks. And each of these formats is supported differently by each hardware type. So, for example, the NVIDIA A100 supports these subsets of formats, the TPU v4, this subset, the H100, this subset, and future hardware will support different subsets. So this leads to an interesting challenge when you're designing neural networks into how to give different parts of that neural network different precisions. And this could be on the layer level, the channel level, or different layer types. And the search space only grows larger with the increasing support of numerical formats. So what is the best way to actually assign these formats in order to maximize accuracy and performance for the network? What I'm showing here on the right is a ResNet 18, and each block represents a different layer within the network. And the first block on the left is the first layer in the network, and the inputs go left to right. And in order to get a nice proxy for performance during these searches, we use BOPs, which are the binary operations. And to calculate the BOPs, you take the number of bits within each layer, and you square it and then multiply it by the number of operations in that layer. And this proxy tracks particularly well for power and area necessary for these networks. And what you find is that different layers within a given network require different precisions, and they have different sensitivities. So for example, within this ResNet 18, and this is actually true for a lot of architectures, the global position of a lot of the layers is important. The first and last layers often require higher precision, and the layer type is also important, where these downsampling convolutions on the skip connection require higher precision. And in addition, individual training runs will give you specific weight parameters that will cause variance in the precisions that each layer needs. So the same network, if trained differently, will require different precisions on different layers. And this leads to large search spaces. So even in the smaller example of ResNet 18, this search space exceeds 10 to the 18 on a larger numerical search space. So what is the best way to search these large design spaces? So the way that we propose, and more details can be found in the paper, is by using a one-shot neural architecture search. So what this means is that we actually search the neural architecture while we're training the network from scratch. So here we have the FLIQS controller, and on each training step, it proposes this new architecture alpha, which is made up of in this case, the number of channels per layer and the format for each layer. And then it does the forward pass, it calculates the gradients, updates the weight parameters, but it also runs the model on validation data, which will be used to calculate the reward to choose the future architectures. So in this case, the accuracy comes in, and the cost represents the actual performance proxy in binary operations. And this is combined into a joint reward, which is then modified slightly and passed to the controller to update its architecture decisions in the future. So this one-shot approach has the benefits of increasing efficiency by being able to search many more model architectures, and not requiring the full training on each of them. But the downside is that the reward signal can often be weaker than in alternatives. But we find it is strong enough for our purposes. So here are some outputs examples from the FLIQS search. On the integer side, this is a ResNet at 50, which I've already really gone through the overall trends. And here's a MobileNet v2. So similarly, the first and last layers receive higher precision, but also this middle depth-wise convolutional layer also gets higher precision. And this is a vision transformer where you see that the key projections often get higher precision, and usually this post-attention linear layer gets a higher precision. And then the same trends are typically true in the floating point case. Often, since MobileNet and the EfficientNet architectures share a lot of similar components, they will have similar trends as well. So now putting this all together on a same plot where we show the ImageNet top one accuracy on the left and the GBOPS performance proxy on the bottom. We list each dot here is a model that has been searched and trained from scratch across different architectures, including ResNets, EfficientNet, MobileNet, Inception, and Vision Transformers. And what you see is that where the top left is better, you'll find that the MobileNet and EfficientNet architectures provide the best accuracy and performance trade-offs. And among those, the FLIQS searched variants, which are in yellow and green, give you the best accuracy and performance trade-off. And with a floating point search, this is also true, where you find that the MobileNet and EfficientNet give you the best, and among those, the FLIQS search models have the best accuracy. And I should say that even within the ResNets and Inception, the FLIQS models do give the best accuracy performance. So then to expand the search, we could take a look at the quantization and neural architecture search, where you simultaneously search the format, the kernel size, and the number of channels within the model. So there are three variants here that should be considered. One is where you fix the formats and you only search the architecture. So this would be a quantized neural architecture search. The second is where you fix the architecture and you only search the formats. This is a quantization search. And then the third is where you search both the format and the architecture at the same time. And what we find is that the joint quantization and neural architecture search provides, well, Pareto dominates the other two methods on this MobileNet v2 search space. So we find that this happens especially at the larger model sizes. So what we're looking at here is that the FLIQNAS with a small search space and with a large search space, Pareto dominates the other methods in terms of accuracy and performance. So overall, and much more details provided in the paper, but FLIQS is the first to combine reinforcement learning with a one-shot search combined with quantization-aware training. It introduces a switchable clipping bound and cosine entropy regularization, which was omitted in this presentation. And it establishes the advantages of low precision floating point, since these models often dominate their integer counterparts, and the joint QNAS searches, which dominate both the vanilla NAS search space and the pure format search space. Thank you.